is called 5.6 Part 2. 5.6 Part 2. And we're going to be discussing the domain of a rational function. Domain of a rational function. And what we know about rational functions is they involve some kind of dividing, right? Rational typically means fraction. And so these functions involve some kind of dividing situation. And when we started these this year, in the very beginning, we were solving rational functions. We were doing a lot of stuff with them. We learned that I cannot divide by 0. If I divide by 0, it kind of breaks the whole thing. And so today we're going to be looking at the domain of a rational function. The domain of a rational function includes all real numbers except those that cause the denominator to equal 0. Okay, so that holds true, that same rule that we learned all year long. I cannot divide by 0. So if we're finding the domain, we're looking for all of the numbers except those that make the denominator equal 0. Pop quiz, what's the domain of a quadratic equation? Quadratic. It's parabola. Domain. Negative infinity to positive infinity. Perfect. All real numbers. What's the domain of a polynomial? Any polynomial. All real numbers. Polynomial functions are continuous. Okay? Rational functions have problems. Real problems. They cannot be divided by 0. So what we're going to see in these pictures is breaks. We called them yesterday asymptotes. They're also known as discontinuities. Discontinuities. And these discontinuities arise when I try to divide by 0. Okay? Discontinuities. We're going to see two kinds today. We're going to see one called a whole or a removable discontinuity. And the other one we're going to see today is called an asymptote. And you already kind of had a glimpse of these yesterday. Discontinuities, they're going to come in the form of wholes or asymptotes. The problem is I can't divide by 0. That's where we see the discontinuity. It happens in the denominator of the problem. Okay, so if I looked back at this that we just wrote on the board, domain of a rational function involves discontinuities, causes the denominator to equal 0. This happens when I try to divide by 0. I'm trying to think of all of the different ways that I can make this happen for you with alliteration. The denominator affects the domain because when I try to divide by 0, there are discontinuities. Are you catching what I'm saying? You understand? Okay, so let's look at example 4. Example 4 says, I find the domain of f of x equals x plus 3 divided by x squared minus 9. Find the domain of f of x equals x plus 3 divided by x squared minus 9. Okay. So a little bit of how-to for you. When I'm searching for the domain of a rational function, I'm going to set the denominator, because that's where the domain is affected. Set the denominator equal to 0. This happened yesterday in pre-cal class. I had a kid say, I almost got this question right. It was on AP pre-cal exam, and it was about asymptotes. And he said, I almost got it right, except I forgot which one was the denominator and which one was the numerator. At this point, I can't help that. That's beyond me. I told him it was the did not and the toperator. Let me just write it down. Number 2, solve for x. Number 3, domain is everything except numbers in step 2. All real numbers except the ones that you found in step 2. You understand what I'm saying? So if we're supposed to find the domain of this function, 1, we're going to set the denominator equal to 0. The denominator here is x squared minus 9. We're going to set x squared minus 9 equal to 0. Step 2, solve for x. You could add 9 to both sides. So x squared equals 9. What does that make x? 3. Or negative 3. Remember, when I square root, I've got 2 options. Plus or minus 3. You following? The domain is everything. That's what that says. Everything. I don't know what happened. This does not say everything. Pretend it says everything. Everything except those numbers from a step 2. So we write it like this. The domain is x such that, that's a vertical line. We practiced this early this year. X such that x is not equal to positive or negative 3. Do y'all remember the curly Q lines? And I gave this to you in set notation. It's called set builder notation. Everything except positive and negative 3. Okay. Now here's another way to look at it. You had x squared minus 9 in the bottom. That could also have been written as a difference of 2 squares. X plus 3 and x minus 3. You following that? If you set each piece equal to 0, you get x equals negative 3 and x equals positive 3. Is that better? Everybody understand domain? Okay. Now the domain is going to tell a story. I'm going to put up a picture here. This is example 4. This is the picture of the problem we just solved. And we said the domain is everything except x equals 3 and x equals negative 3. Notice that at x equals 3, we have a this. What is a this called? A vertical asymptote. This is a vertical asymptote. But look at what we have at negative 3. Is it an asymptote? No. This is what we call a hole. This is what it looks like on a graph. On Desmos, when you blow it up, you can scroll all the way over to the exact point that we're talking about, and it will show an undefined point. It will not show on your TI-85 or your Inspire. You can't get close enough to see the hole. The hole is one tiny, 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 tiny little value. Okay? You're not going to see it on the picture. But on these graphs, they make a point to show you where it is. And on Desmos, it will show undefined. It's not going to show the hole. Okay? So how do I know, based on the function, whether it's going to be a hole or whether it's going to be a vertical asymptote? What I know is it's discontinuous there. The domain shows it's broken. But how do I know the difference? So I want to go back to this function. It was x plus 3 over, and we had x squared minus 9 in the bottom. I'm going to write it in factored form, x plus 3 and x minus 3. Notice that I have what are called common factors here. X plus 3 on top and bottom. Okay, these are called common factors. I also have called them cancel buddies. That's really how I like to refer to them. They're cancel buddies. Buddies meaning they have partners. Are you with me? Okay, so if there is a common factor, the graph will have a hole. If there is a common factor, the graph will have a hole in that location. What was the 0 for this hole, for this factor? X equals -3. Can you see it? If it doesn't have a common factor, it's going to show a vertical asymptote at that 0. X equals +3. Can you see the difference? Okay. Had a student several years ago. Okay. Moving on. So let's look on, this is going to be example 5. Okay, first of all, I want to just talk to you really quickly. This is called a removable discontinuity. That's another name for hole. A removable discontinuity. I told you this earlier. So it's called a removable discontinuity because it feels like I wouldn't have to work very hard to fill the hole. Can you see that? Okay. If I could, and we do this in calculus, we fill the hole. We set x to equal some value so that at that particular spot, there is no discontinuity. It's nice. You can plug the hole. You can remove the discontinuity. Can you imagine filling up a volcano with pebbles? How many pebbles would it take? Like a lot, right? So there's no amount of stuff that I could put in this space to fill the hole. A vertical asymptote is just a discontinuity. It's not removable. But the actual little dot, the hole, I could probably plug it with a number. Do you understand the difference? Okay. So the holes show up on your functions as cancel buddies. So there's going to be a hole on this graph at x equals -1. There's going to be a vertical asymptote at x equals 3. Any questions on that at all? Okay, so let's... How do you know which one's the hole and which one's the asymptote?
Like if you have 2 that don't cancel.
The bottom. Okay, great question. So you have 2 things that don't cancel here. You've got x equals 1 and x equals 3. The asymptotes are always found in the denominator. Remember, I really emphasized that when we first started. The denominator determines the domain because it would be discontinuous when you try to divide by 0. All of those things are in the bottom. Good question. Okay. Nope, I don't want that. All right, so let's look at example 5. Example 5 says, find the vertical asymptotes I think I'm going to actually not do that problem and do this one instead. Find the vertical asymptotes and holes in f of x equals x minus 2 over x squared minus 4. Find the vertical asymptotes and holes in f of x equals x minus 2 over x squared minus 4. So the first thing we want to do is we want to factor the bottom so that we can see clearly what's happening down there. We have x minus 2 divided by, how does it factor?
X minus 2 plus 2.
Okay, x minus 2 and x plus 2. Now do we have any cancel buddies? Yeah, x minus 2 and x minus 2. So what do I know?
X equals 2 is the whole.
There's going to be a hole at x equals 2. And there's going to be a vertical asymptote at x equals negative 2. Can you see it? Any questions there? We understand? So if we look at that picture, I believe is that this guy? No, still not. I tried to take pictures before or during lunchtime, and I don't think I got what I wanted. Nope. Pause. I'm about to grab. All right, let's go on to trying to decide if I want to do the next problem or not. Here's a try it. We've got f of x equals x squared minus 25 divided by x cubed minus 6x squared plus 5x. The question is, where are the holes and where are the vertical asymptotes?
Is that x squared minus 25?
Uh-huh. X squared minus 25. It is a difference of squares. So if you factor the top, you're going to have what, Ashley? X plus 5 and x minus 5. Okay? And on bottom, you're going to factor out one of the x's. That'll bring it down to being x squared minus 6x plus 5. X minus 5, x minus 1. X minus 5, x minus 1. Okay? Any questions there? So we're going to have a hole if we have any cancel buddies, any common factors at x minus 5. So hole at x equals 5. There's going to be a vertical asymptote at any remaining zeros in the denominator. X equals 1 and x equals 0. Many of you missed this guy on your test. You forgot to set that equal to 0 when you were identifying your zeros. Okay. So if we were to graph it, we would see vertical asymptote at x equals 0, vertical asymptote at 1, and we would see a hole when x equals 5. Somewhere in the graph, there's going to be a hole there. Okay? Any questions on that? Say it again. So that's a great question. How do we tell what the horizontal asymptote is? We have the vertical asymptotes kind of nailed down. We know we set the denominator equal to 0. We look for holes. We look for cancel buddies. We do that. How do we find the horizontal asymptotes? That's a great question. So there's three cases for horizontal asymptotes. I'm going to talk to you really quickly about these different options. Okay? You don't have to write this down yet. I'll tell you what to write in just a minute. The first case is this. If the degree of the denominator is greater than the degree of the numerator, there is a horizontal asymptote at y equals 0. Okay? So what that means is if I'm looking at some kind of function here, like 4x plus 2 divided by x squared plus 4x minus 5, what's the degree of the top? 1. What's the degree in the bottom? 2. If the degree in the top or the degree of the denominator is greater than the degree in the numerator, the way that it trends is it goes to y equals 0 as your horizontal asymptote. Can y'all see that? That this is the rule? This is how it happens? I always imagine this. If I brought one donut for this class, I brought you a donut. Are you really happy with me? You think I'm being real generous? Probably not, because how much donut are you getting? very, very little, a crumb, right? So 1 divided by a lot doesn't make very much. If the degree on top is less than the degree on bottom and we're dividing, you're not going to get very much. It goes to 0. Does that make sense? Okay. Here's case number 2. If your degree lies, that's case number 1 again. Here's case number 2. If your degree on the top is greater than the degree on the bottom, weird stuff happens. There is no horizontal asymptote. No horizontal asymptote. There's no limit. Okay, it's just going to keep going to infinity. We'll talk about the slant asymptote stuff next year. I'm saving that for pre-cal. Case number 2, if the degree on the denominator is less than the degree on the numerator, there is no horizontal asymptote. Are y'all good with that? Okay. Case number 3. If the degrees are equal, if the degree in the denominator is equal to the degree of the numerator. So look at this problem right here. What's the degree of the top? 2. What's the degree of the bottom? Also 2. If the degrees are equal, then you compare the ratio of leading coefficients. What's the leading coefficient in the top? 3. What's the leading coefficient in the bottom? So you're going to have an asymptote at y equals 3. Pretty nifty, huh? Okay. So I'm going to put right here the rules for horizontal asymptotes. And you can be writing those down. And then we're going to work through maybe 2 problems in the time that we have left. How'd you do, Coop?
You too.
Okay. Okay, so this is g of x equals, 6x cubed minus 10x over 2x cubed plus 5x squared. And based on the rules, what's the degree of the top and the degree of the bottom? 3. If the degrees are equal, then what do? We go to the ratio of leading coefficients. So the ratio of coefficients is 6 over 2. There will be a horizontal asymptote at y equals 3. I actually think that was Riley. I don't think that was Hudson that said the thing about the asymptotes. I think it was Riley. All right, h of x is equal to x squared minus 4x plus 1 over x plus 1. Now look at the degrees. Top one's greater than the bottom. No horizontal asymptote. No rule here. No asymptote. Last one, k of x equals x squared plus 4x over x cubed minus 8. Horizontal asymptote at 0. Why? The denominator wins. Again, I bring one donut and divide it against a whole bunch of you. You're not getting much. Horizontal asymptote at y equals 0. Good? Is it okay today? Okay. We've got one more. One more. Don't put up yet. We got 6 minutes. We got this. Okay. I'm going to put it all together in one problem. Are y'all ready to move on from this slide yet? No. Okay. No. Please don't do that to us. All right, it says, this is example 9. Example 9, and it says find the vertical and horizontal asymptotes. And our function here is f of x equals x minus 2 times x plus 3 divided by x minus 1 times x plus 2 times x minus 5. Do we have any holes? No cancel buddies. So that means that there's going to be a vertical asymptote at every single piece in this denominator. You're going to have one at x equals 1, at x equals negative 2, and at x equals 5. Cool? Your horizontal asymptote needs to go, look at the degrees. What's the degree on top? 2. It's going to be x squared. If I FOILed that out, I would have x squared. On the denominator, I have x times x times x. That's going to be x cubed. If I have the bottom with more than the top, we're going to have a horizontal asymptote at y equals 0. Okay? Any questions on today? You understand how to find the asymptotes and the holes? Okay, we'll put it all together tomorrow. So come back. You'll learn something new.